Hello, Jacqueline. Hi, Kevin. Hi, Victor.
Hi, Lisa.
Hi.
How are you?
Fine. So do you know in what order you're presenting today?
Yeah, Kitty will go first, then I will go next, and then after that, Logan.
Okay. Jacqueline, do you want to try sharing your screen?
Okay, I'll just check. Give me a minute. Okay, it says disabled.
Oh, wait a minute. That's my bad. Let's see. Okay, so I think I need to make you host. Make you co-host.
Thank you.
Okay.
Yeah, I can do that now.
Okay. Then you can also make, can you also make Kitty
co-host? So you see my screen?
Okay, yeah, that looks good.
Okay.
The seminar last week was wonderful. It got such good audience response.
Yeah, we were glad to see so many participants. Thanks for arranging all of that, and I'm glad you guys liked it. Looking forward to today's session. Hopefully we would be able to, consolidate some more things.
Hi, Kitty. I will make you co-host. There you go.
Okay.
Hi, Jack. Hi, Lisa.
Hi.
You want to share your screen? I'll stop.
Yes.
Yes, I would like to.
Okay, go ahead.
Okay. Thank you. Sure, I have it right here.
Okay, that looks good.
Okay, let me turn that. Oh, where is it? Let's give it. What time is it now? Let's give it another 4 minutes. I'll play some music, then we can start.
Oh,
Okay, Lisa, you can start if you have something to say.
okay, I just wanted to make sure that Logan had a chance to make sure he can screen share.
Okay, Logan, could you please check?
See, I'm not sure. he
Yeah, sure.
can-
Yeah,
okay.
I can. Yeah, I can. It gives me the prompt that says, "Do I want to make sure to screen share?" So yeah, it should work.
Okay,
Sounds good.
so should we just start?
Yes.
Okay,
All right.
let me first stop the recording and,
Oh, it was.
which I can't do.
The recording has started.
No, yes, I know, I'm supposed to stop it and then immediately start it.
Oh,
But because the screen is up, can you please get out of your screen temporarily so that I can shut the recording off and then, okay. Why isn't it?
yeah, it's still going.
Yeah, why isn't it letting me? Why
Can
isn't it let?
I
why
can
isn't-
stop recording, but I don't know.
I just have to stop it and then immediately restart it.
Oh yeah, I think you did it.
Oh, you sure? Does it?
Yeah, it disappeared for 1 second. Then.
All right, okay. Then go ahead.
Okay, thank you, Lisa.
Okay.
I'm gonna share my screen again.
Oh,
So can everybody see the Symphony in F major piece? Okay.
Yeah.
Okay, thank you. So good afternoon. How's everybody doing? I like to thank you for coming to the seminar again. So for those who were not with us last Wednesday, welcome to join us today. We will review some of the content that we covered last time. So you don't need to worry about being confused or left out. You'll be okay. And for those who did come last Wednesday, welcome back. And we hope you had a chance to play some of the natural number game at home. If not, don't worry about it. We are here to help you to complete the addition and multiplication worlds in this session. So here we are again. If you didn't get to meet us last time, so Jacqueline, Logan, and myself will continue to work with you today and in January 2022. Okay, this is our plan for today. We're going to revisit the Melise and Alice puzzle with a focus on pattern of reasoning. After that, Jacqueline will give us a review of the tactics and theorems that are useful for the natural number game. Then Logan will demonstrate a Lean proof using some of the tactics. And lastly, we will use the second half of the session to play the natural number game. It's unlikely we will finish all of the levels. The purpose is to get it going with our help so that you're able to move forward when you're doing it on your own. For those who are already halfway through or have already finished the game, we have more for you to do. So don't worry, you will not get bored. So we will work in groups based on where you're at. I understand we're at different places. So let's start with revisiting the Melise and Alice puzzle. This is a list of conditions for the puzzle. We looked at them last time. I highlighted the locations, the characters, and the attributes of the characters. And in last session, I remember it was Mary, when she shared her thoughts on how to solve it. We talked about condition number 5, victim's twin. There are only 2 possibilities. Either the 2 kids were twins or Alice and her brother were twins. Alice's husband may have a twin, but the twin cannot be in this group. So that should be very helpful for us to sort out the possibilities. Now, what information can we extract from this list? Well, 3 things. First of all, men and women in the bar from condition 1. Second, killer and victim on the beach. And third, child alone. So this shorter list helps a little bit, but it doesn't give us the solution. To arrive at a solution, we need a systematic search, and you may call it reasoning by cases. So let's see what we can do with one of the conditions. For example, men and men in the bar. Let's start there. So if you want to count all the possibilities or all the possible situations, there are 6 in total. Alice was with her husband, Alice was with her brother, Alice was with her son, the daughter was with Alice's brother, the daughter was with the husband, the dad, and the daughter was with the son. And however, we were told that Alice and her husband were not together, according to condition 4. We were also told that the kids were not together, according to condition 3. So now the possibilities are reduced to 4. And we can examine each of them more carefully. So I suppose Alice was with her brother. And then who had to be on the beach? The husband was with the daughter or with the son at the beach. So here are another two possibilities. We can call them case 1.1 and case 1.2. And condition 6 says that the killer was younger. So in these 2 cases, either the daughter or the son has to be the killer because they're obviously younger than their dad. However, condition 5 says the victim's twin is innocent. And this means that the husband has a twin and the twin is in the group. This is a contradiction. So now you see that the first case we just looked at is an impossible situation. And we can move on to the next cases and examine them in the same manner. Sooner or later, you will get to the right answer. So that's the method, or We call it systematic search. Of course, you may start off with a different fact. You can, for example, all possible situations considering Alice and her husband were not together. It also works. So if Alice was in a bar, then her husband was at the beach, or the other way around. So you can figure out that way. So then you list all the possibilities and eliminate some of them when a contradiction is reached. So now the question is, what can we learn from the puzzle? Here are a few things that I'd like to have your attention. So in your handout, I'll put in the chat in a minute. So you will see some examples using key logical terms in the Melissa and Alice context, such as if then, if only if, conjunction and disjunction. So before we move on to the next section, I would like to draw your attention to these two statements. They're slightly different. Philosophers are very interested to study the second case, but mathematical logic is concerned with the first one. What's the truth value of this statement? I mean, the first one. Well, since it is false that I have two heads, the statement, if I have two heads, then circles are squares, actually comes out true. It is counterintuitive, isn't it? So this is why we cannot always trust our senses and intuition. We need logic to help us reason and think clearly. So I hope you learned a few things from the puzzle. When you have mushy thoughts, try to sort things out in a systematic way. So that's the lesson. Now I will hand the session over to Jacqueline. She will introduce and explain some of the tactics that you'll be using today. Jacqueline. Oh.
Thanks, Kitty.
Thank you. Go.
All right, so we'll be reviewing some tactics and theorems in the addition and multiplication world on the natural number game today. But before we go into that, I'll be quickly reviewing the 5 piano axioms of number theory, which we actually covered at the last session. So it's basically for those who did not join, or also a quick revision for those who were there already. So the first one being 0 is a natural number. The second piano axiom of number theory being every natural number has a successor in the natural numbers. Third is 0 is not the successor of any natural number. Fourth one, which is also called the principle of injection, is that the successors of two natural numbers are same if and only if the two original numbers are the same. And fifth, which is also called the principle of induction, states that if a set contains 0 and the successor of every number is in the set, then the set contains the natural numbers. So when we begin in Lean, one of the initial steps is to import MyNat definition, because that imports piano's definition of the natural numbers. It gives us the term 0, so 0 as a natural number. And also that will give us a function suc, which is defined from the set of natural numbers to the set of natural numbers, and wherein the suc n would be interpreted as the number after n. So it's basically the successor. And it would also give us the principle of mathematical induction. So this is a critical step to do in the beginning when you start working on Lean. Now let's review a couple of tactics that Logan reviewed last time in the first session. So the first one being reflexivity. I think you guys would already know about this property. So it is in Lean, it is used to close a goal of the form P equals Q. So however complicated P and Q might be, the main thing is that the left-hand side should be equal to right-hand side. And then you can close that goal using the abbreviation REFL, R-E-F-L. So that's how it looks. So it's 1 + 1 + 1 = 3. So you just use that and that closes your goal. Coming to the next tactic that we discussed last time, rewrite. So the abbreviation for that is RW. So if you're given a hypothesis of the form A equals B, it basically just replaces the occurrence of A with B or vice versa. So you can say it's used to substitute in the values of variables in simple language. So if I have a theorem.
Can I ask a
Yeah.
question? This is it built into this this rewrite or this REFL certain rules which need to be proved, such as that A plus B equals B plus A, for which you need the fifth axiom. I mean, if you take out that axiom, you can't prove that. Is that sort of built in, or what's the status of that
So
type
if you
of
have,
replacement?
thank you for the question. That's a good question. So if we have something like A plus B equals B plus A, there's another theorem that we'll be using in a combination with the tactic, and I'll be reviewing this after that. After this one. But rewrite is basically just to substitute in, and reflexivity is when left-hand side is exactly equal to the right-hand side. So it would work when you have A plus B equals A plus B. Thank you. So here, looking at this theorem, if you have A, B, C, D as natural numbers, and H1 is defined as a hypothesis A equals B, and H2 is defined as C equals D. And if I got to prove something like this, A plus B plus C equals B plus C plus D, then what I'll do is I will be using the tactic rewrite to use H1 first. So you see what that does next? It replaces A with B here. Now I see I have B plus C equals B plus C plus D. So I want to replace either C or D. So if I use rewrite H2, it would replace C with D. But if I want to use it the other way, that means if I want to replace D with C, I'll have to use rewrite with the left arrow. So that gives you B plus C equals B plus C. And now is the time when you can actually use reflexivity. I'll share later how to get that left arrow. So coming to the new tactic that we're going to learn today is for the induction, is induction N with DHT. So that will attempt to prove the goals by induction on N, and with the inductive assumption in the sub case being HT. So you know how we use induction in mathematical proofs usually, right? So you prove it for N equals 0, and then if we assume for N equals K, and that implies the case is true for N equals K plus 1, then we say that it holds true for all N, for all natural numbers. So likewise, what this tactic does is it will turn your goal into two goals, a base case with N equals 0, and another one would be an inductive step, wherein HT is the proof of the N equals D case. And your goal would be N equals suc D case. When I say suc D, I mean successor of D or D plus 1. So it's exactly the same. It's just the lean way of saying it. Coming to the proofs of theorems. So we reviewed the tactics so far. These are the theorems. So when you use a theorem with a tactic, you actually use the proof of the theorem. So it's really important to use a tactic with the theorem. So we'll see how we do that. First one being add 0. So I really like the simplicity of the names of the theorems in Lean. If you look at this, it's simply an element adding 0 to it, right? So that gives you A plus 0 equals A. So you already have add 0 as a theorem, which you can refer to. So if I need to simplify A plus 0 to A somewhere, I'll just simply rewrite add 0, and that gives me A in place of A plus 0. Now coming to the next one, 0 add, again, going by the name. So 0 comes first, and then you're adding another element. So use it with rewrite again, so that we are actually using the proof of the theorem. So this simplifies 0 plus A to A again. Coming to the next one, which says add suc. So again, you're adding a successor to an element. So that's A plus suc B, which means A plus the number, which is next to B. And that gives you suc A plus B, or successor of A plus B, or A plus B plus 1. That's the understanding. So again, you'll be using that with the rewrite tactic. So it's just substituting in this value. Now coming to the next one, suc add. So that has successor first, and then you're adding to B. It again gives you the number which is next to A plus B. So again, look at the simplicity of the names so that you can even predict later on, even if you don't know what it has in, you might be able to predict. Now coming to the next proof of the theorem, which is addition is commutative. So add-com is actually, it would give you a plus b equals b plus a. So using this with the tactic rewrite, what it will do is it will just find the first case wherein two numbers are being added and it just swaps it around. So if you want to target more specific additions, for example, you just want to swap something which has the first element as a, then you would use rewrite add com a. So what it will do is it will go in the same order as it is written, and then the first term that it sees of the form a plus something, it will just swap that around. Likewise, if you want to just target something which has a and b both, then you can rewrite add com ab. So that will only swap additions of the form a and b. So you have these kind of ways wherein you can target something specific. And then if you want to just do the right commutativity, so you use add right com, that would give you a plus b plus c as a plus c plus b. So that does the commutativity on the right side. Next, we have the associativity of addition. So addition of natural numbers we know is associative. Add a sock will give you, the left associativity. So a plus b plus c changing into the right one, a plus b plus c in brackets. Again, you use it with the tactic rewrite, and to change it back the other way, so from right associativity to the left one, you use a left arrow again. So you can get the left arrow by just typing /L. This is small l. It looks like 1, but it's small l. And then a space bar in Lean. So that will take you that way. And we also used it in the past. So yeah, you do it the same way. Now, one thing to take care of is that Lean, it automatically interprets left associativity. So if you don't see any brackets, if it's just written as a plus b plus c, it will automatically mean that it's left associative, a plus b in brackets plus c. Now let's have a quick look at some of the proofs of theorems in multiplication. So again, you would be using import mynat.mul to import the definition of multiplication on natural numbers in Lean. Again, something as simple as this, mul0, that means you're multiplying with 0. So an element or a number multiplied with 0 will give you 0. You'll again be using it with rewrite. Then 0 mul, it's 0 multiplied with a number, giving you 0. Then you have mulsuc. So you're multiplying a number with a successor. That means a multiplied with a number which comes next to b, and that would be equal to a times b plus a. I think we looked at a lot of tactics, so we can pretty easily make some educated guesses here what mul1, 1 mul, or suc mul might give, right? So mul1, you're basically multiplying a number with 1, so a times 1. Then 1 mul, it's 1 multiplied with a number. And suc mul, so successor come first, and then you're multiplying with another number. The last one is addition is distributive over multiplication, so the distributive property. So we can use add mul here. That would give you a plus b times t as a times t plus b times t. Now we also have the commutativity and associativity in multiplication, and you'll go over them in the natural number game worlds, the multiplication world. I'll just pass it on to Logan now, and he'll show us how to use these tactics and theorems in Lean hands-on.
Great, thank you very much, Jepleen. I'm just going to share my screen so that you can see my text editor. Okay, so I am going to give a proof of this theorem that uses rewrites and reflexivity and induction and all that stuff. Before I do that, I quickly want to address a conversation that Callum and I were just having in the comments of the chat, talking about basically sort of how reflexivity works and maybe why it works in some cases, but not in others. So Callum's question was basically, it seems like reflexivity should only work when the term on the left-hand side and right-hand side of the equality sign are exactly the same term. And this is absolutely true. This is something that reflexivity can prove. And this is a very tight case. This is a very unique case called syntactic equality, where I have 3 on one side of this equation and 3 on the other. And obviously these are the same term, so reflexivity obviously holds, and that's used to close this goal. The example that we gave in the slides of 1 plus 1 plus 3, or sorry, 1 plus 1 plus 1 equals 3 is not syntactically equality, right? Because the term 1 plus 1 plus 1 is not the same thing as the term 3. And, if you look at how Lean interprets those terms, the syntax tree is different if you look at the encoding of natural numbers. But what it's using to use reflexivity is something called definitional equality. So another example here is I have a theorem that says that any natural number n times 0 is equal to 0. And I can prove this using reflexivity. What I can't do is I can't use reflexivity to prove that for any natural number, 0 times that number is 0. If I try to do that in this proof, reflexivity fails. And that's because this equality is not definitional. This has to be proved using induction, actually. But using it has to be proved as a theorem. It doesn't follow from the definition of multiplication. So in fact, if I look at, I can go where I've written nat.mul. So this is multiplication of natural numbers. I can ask Lean to show me the definition. And so the rest of this is just noise. But looking at this piece of code in particular, you see that multiplication is defined by recursion or by induction on the right-hand variable, the right-hand operand. And I see that by definition, any natural number times 0 is equal to 0. So this is definitional equality. If I had defined multiplication the other way, so that it says 0 times any natural number is also 0, then I could prove this other version of it. But because basically Lean knows how to resolve this equality using the definition of multiplication, that's why this can be closed by reflexivity, but this can't. So I hope that sort of gives some intuition as to what definitional equality is, and then sort of what it means for Lean to superficially know that these two terms are equal despite not being syntactically equal. So leaving that as an aside, the main part of this demonstration is going to be this theorem here. It's the successor mul theorem. So it just says that the successor of A times B is the same thing as A times B plus another instance of B. So for instance, 4 times 3 is the same thing as taking 3 times 3, which is 9, and then adding another 3 on top of that, which is 12, which is 4 times 3. So you should be convinced that this is a true theorem, which is good because now we're going to prove it. So I'll begin by using the induction tactic. So I'll do induction on B, and I'll introduce the names K and IH. So K is going to be basically the new name I get in my inductive case. So my base case is going to be where B is equal to 0, and my inductive case is going to be B is a successor of K, and then my inductive hypothesis is going to be that this equality holds when B is equal to K. So I'll start with the base case. So looking at my little info view here, I need to prove that the successor of A times 0 is equal to A times 0 plus 0. So I know that anything times 0 is 0. So I can do a rewrite of that theorem, which is listed up here, mul 0. So I'll do rewrite mul 0. And that takes care of the first instance. So successor of A times 0 simplifies that to 0. And then I can do the same thing with A on the right-hand side. And because I'm using Lean that's installed on my computer, so in the natural number game, because the rewrite tactic is slightly weakened, you would have to finish by using reflexivity of 0 equals 0. But the version of Lean that I'm using, whenever I do a rewrite, it automatically tries to close it with reflexivity. So you can kind of imagine that this is just an invisible invocation of REFL here in the base case. But those two rewrites of mul 0 are all I really need with reflexivity. The inductive case takes some more work, and I have to use a couple of different rewrites of different theorems. So I have successor of A times successor of K is equal to A times successor of K plus successor of K. And my inductive hypothesis is the same sentence. I just take away all the successors of K. So I want to start moving around the successor function, and I want to move it around with respect to multiplication because I want to get either of these sides to a form where I can rewrite with my inductive hypothesis. So I'll look at what I have. I have mul suck here, and I have suck mul, which is what I wanted to prove. So let's see if I can use the one that I already have, which is mul suck. So you'll see that it looks and it finds the basically it unfolds a definition of multiplication. So it's basically going to take successor away from K and then add successor of A onto the right-hand side of that multiplication. And actually, if you see here, if you look at just the right-hand side of this sum operation, I get exactly the left-hand side of my inductive hypothesis. So now I'm going to rewrite the inductive hypothesis. So I can rewrite not only previously proved theorems, but also my assumptions in my proof context. And then I can keep going. You know, if you parse this a bit more, you can see that I need to do some more instances of mul-suc. And then I need to, now that I've got all my additions here, I need to start playing around with the addition successor. I'm not going to spend too much time going through this. If you like, we can talk more about this proof after. I need to do add suc a few more times. Oh, one time too many, sorry. I need to use, so here, oops. Here you can see that I'm getting pretty close. I just need to sort of rearrange the terms here. I'll actually use the associativity of addition. And then I want to use, I basically just want to swap A and K here, because then I get something that's equal to this term here. So I'm going to rewrite add com. If I just do that naively, it totally messes up the equality and I get farther away from what I want to prove. So I'm going to follow Jacqueline's advice and specify which variables I want to swap. I want to swap K and A. And then I just need to do associativity one more time in the opposite direction. So I do my left arrow, and then that should complete the proof, which is great. Now, the last thing I'm going to show before we head off into the natural number game is another tactic that I haven't showed yet. And I don't think we'll get far enough in the game to use it today, but I think it's pretty cool. So I kind of want to show it off. And this is the simplification or simplifier tactic. So if I look here, I've done a bunch of rewrites of theorems, and that's pretty much it. I haven't done any sort of like, real propositional logic tools. I haven't done any case analysis. I've just done a bunch of sort of swapping equations around. So what I can do to sort of help simplify this proof is to basically tell Lean that these are some lemmas that I want it to try to use on its own without me guiding it. So to start off, I'll start by saying, okay, you know what, this base case, I just do 2 rewrites of mul0. I want to simplify that into one tactic. What I can do is I can go to my mul0 theorem. I add this decorator that says to use this as a simplification lemma. I go to my base case and I can replace both of these with one call of simp. So it basically knows, okay, I'm going to iteratively try to apply this lemma to simplify, whatever this goal is. And since that's the only lemma I need, then it can do it in this case. And I can do the same thing here. So for example, if I look at add suc and mul-suc, I can make both of those simp lemmas. And then I can take out all 3 of these rewrites in this proof. Wait, oh, I can't get rid of the associativity. And then my proof still works. And I can start getting really crazy with this. So I have mul-suc already. I can't do this whole simplification here because in addition to my simp lemmas, I need my inductive hypothesis. But I can temporarily add the inductive hypothesis as a simp lemma, and then it'll do all that simplification. If you look at what the original one is here, and then all that simplification here. So you can see that it shortens the proof quite a bit. Okay, so that's everything I wanted to demonstrate. So I'll stop sharing. I hope that was interesting and instructive.
Thank you, Logan. That was great. That's a lot of explanation, and it's good to compare and contrast so they know the differences. Thank you. So at this point, let me quickly show what we're gonna do next. We have about 20 minutes. So we're gonna work on addition and multiplication worlds in groups. using the first 3 tactics. You only need these 3. Don't worry about simp. If it overwhelms you after Logan's introduction, don't worry about it. That's a shortcut. You can learn about it later on. The first 3 would be enough for you to handle the first the two worlds I circled. So I think we're gonna work in groups. If you could let us know if you want to work with Logan, which means this a more advanced group, you look at this picture. So if your natural number game looks like this, it's all green dots, that means you're finished. If you're one of those, let's gather your names. So Lisa, maybe you could help manually set up breakout rooms. One group with Logan, you can work on advanced proposition world, or Logan, you have more from Kevin Buzzard based on what they want to do. Let them vote to see what they want to do. And so there's always more for you to do outside the natural number game. And then another group, the rest of us will be working together on these 2 worlds, the more basic, or we can move up to more advanced based on your level. So
instead of manually assigning, maybe we can just create 2 rooms, room 1 and room 2, and students can
do that.
choose themselves.
We do advanced, and the other.
Does anyone know how to create breakout rooms? Because I
can do that.
Thank you. Thank you. So I just have to tabulate names of who wants to be in which group, the basic group or the advanced group.
I think you can I think when you make the breakout room, you can indicate you want to let people choose the room.
Yeah.
Right.
You can give them options.
Creating 2 breakout rooms, and participants can choose from that. And so those who want to go for an advanced level, they can choose room 1, and those who want to try more, discuss more about the basics, they can choose room 2.
Yeah.
Okay.
I'll move into room 1, and then I'll give it a minute or 2 for people to decide.
Yeah, and Kitty and I will be in room 2.
Great.
Right. Logan will be the teacher in room 1. Jacqueline and myself will be in room 2. And let's work together. Let me stop sharing. Jacqueline, I don't see rooms yet.
Oh, there are breakout rooms at the bottom of my.
Oh, there I
screen.
see.
Okay.
So those who are still in the main room, please choose room 1 or room 2. Room 1 is for more advanced practice with Logan, and room 2 is for more discussion around the basics on natural number game with me and Kitty. Kevin, Victor, Paul, Hua, how are you? I hope I'm pronouncing the names correct. Wuhan and Junian. Please choose your rooms.
People are still in room 1, I think.
I closed 2 rooms, but it will take few seconds for them to
Okay.
come.
Thank you. Natural number game.
I would like to put back the link to the survey,
Okay.
which at the
Oh,
moment.
you
the-
did earlier.
I did, but I don't think people can scroll to it at this point.
Oh, maybe it's too far away.
Yeah,
Um,
I think there's been too much.
no. Oh,
There's been too much stuff. Oh, no, it is still there. Okay.
Yes, yes.
I got it. Okay.
there.
So
Is it pretty
please.
bad?
Oh,
Not yet.
so please scroll up and find.
To call them back.
Oh,
Everybody back. Welcome back. Is everybody back? Good? Okay, it was great. How was the group working in room 1? Logan, you want to have a few comments?
Yeah, it was great. So we didn't do the natural number game. We were doing the logic sheets that Kevin Buzzard had written up. And we were talking about sort of some of the ways that Lean's logical system is sometimes counterintuitive to beginners. So we were looking at, the way that Lean treats negation is a little bit strange for people who haven't seen before. And also a little bit for how you reason about implication in Lean the same way you reason about like functions. So we got to talk a lot about that, and I hope it was interesting for people who were there.
Yeah, let's hope. The 2 students, Jiayu and Victor, were working with Chaplin and myself, and they were working on 4 levels of tutorial world, and we finished it completely. Finished the world, and it's good that you guys showed some enthusiasm to the game, and come back in January, because we will have the next session in January, and so we can do more things together. And Logan will be happy to work with you on more different proofs outside the natural number game. And we also will show you how to prove something or theorems using proof by contradiction. It's in the curriculum. If you're undergrad math students, you have to know that proof method. So we'll show you a really nice proof how that can be done in Lean.